So our last speaker tonight is Matt O'Malia. He's an executive partner at Opal Architecture and the co-founder of TimberHP by GoLab. Matt is an award-winning architect with a nationwide reputation for innovation and expertise in the design of high-performance building. A leader in passive house design in North America and named to Architecture Magazine's Architecture 50 list in 2012. Matt is also a co-founder of TimberHP by GoLab, a startup creating the next generation of renewable, recyclable, and non-toxic building materials. He holds a bachelor's degree in environmental design from Miami University in Ohio and completed postgraduate studies in architecture at Frankfurt, Germany. Did you guys cross paths at all?
We did.
You did? Oh, cool. I was totally guessing.
Just now in terms
Oh, okay. It's worth a shot. Mark was the only person when I asked via email for a pop culture reference. I didn't give him enough, poke him enough. I didn't give enough leads. So I got him this morning or this evening, and he said Mark Kelly's book Endurance. He really, really enjoyed, which is great. And so I'm going to pass it off to you. And the title of your talk is Buildings and Forests: How Maine's Resources Can Be Used to Fight Climate Change. And that is yours.
Great. Before you start the clock, I just want to say it's great to be here, and I'm amazed by the speaker panel that I'm at the end of, and I'm a little intimidated. So if I totally drop the ball, it's because they're awesome, and I'm okay. And the other thing is, it's important to note that it's good we have a 5-minute bell because I can go on for hours once I get started because I'm quite passionate about this. And the second thing is I can't remember what slides I use. So if I talk about bunnies and I'm showing a paper mill, just go with it. Stay with me. All right, so Matt O'Malley, I'm an architect, and as an architect, I have this issue with the amount of energy or carbon that buildings emit relative to the total emissions. And on a daily basis, I draw lines. Those lines have an impact on carbon, whether it's both the operational carbon impact because of the performance of the building over time, or it's the carbon used to make the materials in the building. And as a passive house practitioner, I was focused on the 39% of carbon emitted by operational carbon, so operating a building over time. So passive house is a standard which proposes to reduce the energy consumption of a building by 90%. That's like 200 miles to the gallon for cars. So we're talking about the Tesla equivalent of buildings. We were the first passive house firm in Maine. We certified the first passive house in 2008. The 12th in the United States. In the meantime, millions of square feet of passive house have been built. It's sort of a hockey stick adoption, and it's all a result of the imperative around climate change. So when we look at the dynamic going forward, is we're getting good actually at reducing operational energy, both through increased insulation, improved mechanical systems, renewable on-site energy production, and so forth. And as we look out over time, we're going to actually flatten our curve of cumulative operational carbon because we'll get to net zero at some point, as will be mandated by law. But then you see the carbon footprint of buildings is going to be more and more impactful. And that's where an unlikely architect and a chemist who was practicing at UMaine came together to start to solve the yellow part, which is life cycle carbon. All the insulation products on the market until now in North America are, with a few exceptions, high carbon footprint materials. They're made from non-renewable sources. They're completely non-recyclable, in many cases derived directly from fossil fuels. So when we're using insulation, we're trying to save carbon, but actually we're just trading one environmental problem for the other. And as a practicing architect, I realized that the means to the method weren't in alignment with my values and goals. So that's when we started looking abroad. I went back to Germany where I was trained, and we came across insulation made from wood fiber. It's a renewable, recyclable, non-toxic alternative, and it's scalable, meaning it's cost competitive as the others, but it's not made domestically, it's not made in North America, and as Josh, my co-founder at TimberHP, the question we tried to answer is why isn't that so? The simple fact is there's no reason why that isn't so because we live in a sea of trees, which is a renewable resource and carbon storing. In Maine, we had 6 paper mills leave the state in 2016, which had a net negative impact on our economy of $1.6 billion annually. The Madison mill, which is shown here, was shuttered in 2016, a very profitable mill, but due to global circumstances and decline in paper market, it was closed. So we have this incredible resource, which is renewable and recyclable with our forest products, but we have no value-add stream. We've lost jobs and had a severe economic decline in the state of Maine because of it. We came in 2015 and decided that we were going to try and do this ambitious project to manufacture wood fiber insulation domestically, which we've done. As you can see here, we've bought this mill in Madison. We've completed a $130 million financing for it, and we're in the process of building that facility out. We're going to be in production in 2023. We're going to be able to utilize Maine's forest resources, which are primarily 90% FSC certified. In a state where it's underutilized, our regeneration rate is 30% above our utilization rate, which means we have a lot of capacity to sustainably harvest this insulation, and we can have, thereby using this, a massive impact on buildings. And the great thing about this product actually is it uses the residuals from the lumber industry. So the little tiny bits from the round log when it goes to square, all those little pieces of chips that used to go to the paper mill, we'll grind them up into a fiber and make a product out of that can be used in buildings, which we'll be bringing onto the market next year when we complete our build out. I think the opportunity that we saw was that there was a problem out there that had to do with climate, and it started with buildings, but we realized that it had legs into our natural resource utilization. It had a huge impact on our economy, and it had a huge impact on the opportunity to make buildings much more sustainable using insulation that's carbon storing versus high carbon footprint. And we've had incredible support from the state of Maine and investors to get us to this point, and we're really excited that through unusual and unlikely collaborations, this sort of thing is possible in the state of Maine, which I think is unique. Thank you.
I was wondering, in your product, like in your insulation, is it just like wood and wood fiber, or do you add anything to it?
Great question. So there's 3 products, to your point. There's a loose fill, which is a replacement for cellulose, so a blown in. Cellulose is ground up newspaper. There's a bat, which is a stud cavity insulation, which has an adhesive strand made out of polyester by 15% by weight, gives it that flexible quality, but it's just the wood fiber. It also has borate, which is a fire retardant, so that it's non-combustible. And then the third product is a board or a continuous exterior insulation. It has essentially 4% of Gorilla Glue in it and wax. So much like if you know what OSB is, Advantech, it's an exterior sheathing product that's water resistive. It has those same properties. So primarily wood fiber by 95%, but there are some additives based on those different properties of the insulation products.
Over here.
Hi. I'm just curious what the bottlenecks are, what the biggest bottleneck is for the implementation or the expansion of this type of insulation in homes.
That's a great question. The original bottleneck was the Atlantic Ocean because it's expensive to ship insulation. Insulation is very high volume, low value. It's the exact opposite of an iPhone. Can't ship it around the globe. And so to import this renewable material wasn't possible. Not to mention that the cost of lumber in Europe is about 3 to 4 times higher than it is here. So it was a sort of premium sustainability product. We'll be producing it cost competitive with standard insulation. And to your point, we think therefore it's going to be a completely viable drop-in replacement because there's no cost point difference, but you have the advantages of the sustainability and handleability. Insulation is known to be itchy. This is obviously the byproduct of cutting and handling is sawdust, so it's very comfortable. But great question.
Very quick, thank you. Quick follow-up on that, if that's right.
Sure.
So this is being applied to buildings that are being made new buildings, or is this being applied to buildings as a replacement?
That is a great question. So one of the building science characteristics of wood fiber insulation that's important to note is its vapor permeability. It's like Gore-Tex. It allows buildings to breathe, and buildings like humans need to breathe because there's internal moisture generated and there's organic material creating the building shell. And if you put an impermeable layer, like a human wearing a raincoat made out of rubber, you're going to trap moisture, and you know what that does to your skin. Buildings are the same. And so this material is vapor permeable, but it's water resistive, like Gore-Tex. And so it's an important opportunity to use that in renovations because we have incredibly low value in terms of thermal performance housing stock in the state of Maine, and to be able to increase their performance as a way to mitigate climate change is critical, but you have to do it with the right materials. You have to do it with vapor permeable materials, otherwise you'll trap moisture and rot the buildings you're trying to save, which is a huge issue.
I understand that it's cost competitive, especially in like the state of Maine, but how does it hold up on a practical scale? Because I mean, the point of insulation is to stay warm. I'm wondering how your model is compared to like a similar non-biological matter.
Right, great question. So it's an open cell insulation in this case because it's wood versus a plastic, which can be closed cell. So the R value, if that's a familiar term, the resistive value is R4 per inch, which is similar to some of the foams. Some higher performing foams are R5 with the closed value. But what we look at really is the fact that those closed cell foams have an aged value because the blowing agents, which actually have a huge global warming impact, they actually seep out over time, which gives them the increased R value, and it's replaced with atmospheric gases, which drops their aged R value back to what we are here. So in general, they're very competitive, both from a performance and a cost standpoint.
Around when do you expect this to be like on the market, ready to be put into houses?
We're hoping, if all goes well, this time next year for the first line. The loose fill is a very simple process. Then the bat, which is a composite line, which is slightly more complicated. And then the third quarter of next year, the board line, which is, certainly large-scale manufacturing. It's very big. We're manufacturing in the Madison Mill, which is 200,000 square feet. So this is extremely large-scale. Like it's about, the manufacturing equipment is about a football field long. So it's extremely large scale.
You got the equipment from Germany, right?
Right, so our fortunate event was that we were able to buy a used equipment line and import that to reduce the capital costs of our project to be able to kind of realize this new technology in the United States. There. Okay.